Okay, in this tutorial we're going to work on a slightly more complex optimization problem than we had with the boat builder. We're going to use the Burger King example. This is a menu selection problem. This is really one of the classic ways to learn optimization modeling because it's one that everybody can understand. In this context, we're going into a restaurant and trying to place an order. We want to get certain things out of this meal, and I've listed those down here. We want to get certain nutrients, for example. We're trying to order a meal and we want to get vitamins, calcium, iron, but we don't want to get too much bad stuff. We want to limit the calories, sodium, fat, for example, and we're trying to place this order in the least expensive way possible. So that's what a menu selection problem is. Let's look at this Burger King example. I have numerous Burger King products and they're organized by columns. So here I have Whoppers. All right, so this is not necessarily accurate data, but data that I made up. A Whopper price 99 cents, and here's how much bad stuff a Whopper has: 630 calories, 850 units of sodium, this much fat, etc. And the Whopper has some good stuff listed down here as well. So I have a number of burgers, each with their attributes and price. I have, for example, salads. There are two types of salads: broiled chicken and garden, and there are two types of dressings. Each of those has a certain price and certain attributes. Of course, dressings come for free. You can get one if you want with your salad, but they differ in terms of how much bad stuff they have, how much good stuff. And I have drinks, etc. Okay, so we're going to go through and try to optimize our menu selection. Our goal, first of all, let's walk through the elements of an optimization model. What are we trying to optimize? Right here I have the cost of my meal. That's my objective function. I'm trying to minimize cost. I want to find the least expensive meal possible that satisfies all of my nutritional requirements. Right? So I have constraints. If I just want to minimize cost, I can order nothing at a cost of 0. Right? But I can't order nothing because that doesn't give me enough vitamin A, enough vitamin C, etc. So if you look at this sum product in Y13, you should be able to understand that that calculates the cost of the meal based on the decisions that you put up in the red cells. Okay, and again, similarly, you can look at all of these sum products for the constraints. You should understand that this calculates the calories of a meal. So if all I order is a strawberry shake, this sum product tells me that my menu order is $1.29, and now all of my nutritional information has been calculated for that single order of a strawberry shake as well. And again, I put some if statements here to show when certain constraints are violated. For example, a strawberry shake is not a feasible order here. It doesn't give me enough vitamins, etc. It's a very inexpensive order, but not feasible. So let's solve this. Again, we'll go to the Data tab. I have all of the formulas in the cells, so we can go directly to Solver. We can tell Solver, what's my objective here? Well, that's my objective function right there. It's the price of my meal. I want to minimize it. If you forget and leave this maximized, you're going to get a very unusual order, trying to spend as much money as possible. So we want to minimize the cost of our meal. What are my changing cells? Well, this is where I'm going to put how much I order of each item. That's my decision in this menu ordering problem. How many Whoppers I order, how many coffees, how many milks, etc. Now I have constraints. I need to add, I have this bad stuff constraints, right? So these three cells calculate the bad stuff, and these need to be less than or equal to these constraints that I've given myself. I don't want any meal that has more than 1,000 calories, more than 2,400 units of sodium, more than 33.3 fat. If I want to immediately add another constraint, I just click Add. It gives me another input box. Now I have my good stuff. I want these to be greater than or equal to. I need to change this. All of these, and I've decided that I want any menu item, any menu choices that I make, that my order has to have at least 40 units of all of the good stuff. Okay? Now I do want to make my unconstrained variables non-negative, right? There's no such thing as ordering a negative number of drinks or burgers, etc. So I'm going to check make unconstrained variables non-negative, and let's solve this and see what happens. Solver found a solution. All constraints and optimality conditions are satisfied. Okay, that looks good. So here's my order. Order half a Whopper, half a hamburger, 5.3 light dressings, half a milk, etc. You get the point. This solution makes no sense. I forgot to tell Solver one important thing, that I can only order integer amounts. I can't order half a Whopper. I can't order 0.3 chocolate shakes. Right? These numbers are not valid. I need to tell Solver to only consider only consider integer solutions. So let me show you how to do that. Back to solver, it's another constraint. Add the constraint, and this constraint is on my changing cells themselves. I need to tell solver these changing cells right here must be, see this int, integer. That means when you're solving, only consider integer solutions. Now when I do integer, this is called an integer program or an integer optimization model. When I do these, I always need to do one more step in solver. I need to go to options and look at this integer optimality. If you have older versions of solver, this might be called tolerance. I need to set this to 0. Integer programs are very difficult to solve. So if you have a very large one, you might want to tell solver, if you can show mathematically that you're within, say, 5% of the optimal solution, you can stop. We don't want to stop until we get exactly to the optimal solution, so we set that to 0. Click OK, and let's solve it now. Found a solution. All constraints are satisfied. Now I get a solution with integers for all of my orders. We'll talk about several things. Your solution might look slightly different. That's okay. We'll talk about that in a moment. First, let me mention, you might be thinking, well, with the boat builder, we also wanted integer solutions. You can't build a fraction of a boat, but we didn't specify integer on that one. The reason is integer programs are very, very difficult to solve. In this class, this is a business course, so we're not getting into the mathematical algorithms to solve these models. But I can tell you that when integer constraints are involved, it's a much more difficult thing to solve. So we always try without the integer constraints first. If we get an integer solution, so without the integer constraints, it's checking all solutions, integer, non-integer, everything. If it gives us an integer solution, that's fine, we're done. So we didn't have to impose that constraint. It found an integer solution anyway, or the best solution was an integer solution anyway. But if we try it without those constraints and we don't get integers, then we have to go in and specify integer specifically. And this is important. It's important to try it without first. If you're solving models with several hundred, maybe several thousand constraints, and you try to make all of them integer, it's going to be very difficult to solve, even on a very fast computer. I've worked with optimization models with companies with 30,000 or more decision variables. It just wouldn't have been feasible to constrain all of them to be integer. Okay, so now for this selection, we had to say integer. I got a solution $2.87. If you look at this, it satisfies all of my constraints. Doesn't have too much of any of the bad stuff. Has all the good stuff that I need. Now, an important thing about these solutions from Solver is I can tell you without a doubt that $2.87 is the lowest possible price that I can get this price and still satisfy all the constraints. There might be multiple ways to get $2.87. For example, your solution might not have the light dressings. Look, light dressings don't cost anything, so I can subtract those out. I still have a $2.87 order, and I still satisfy all my constraints. Right? So that's another optimal solution. More advanced packages might show you all the possible optimal solutions. Excel is going to mathematically prove that $2.87 is the best price that it can get, and it's going to show you one optimal solution. There may be others. Okay, so let's take a look at this quickly. I want to talk about slack. On the slack here, all I've done, if you look at this slack column, how I've calculated this is it's just the difference between the maximum that the constraint can be and how much I actually have in this solution. So I could have had up to 1,000 calories in my order. It turns out that I only have 670. In other words, the slack is 330. What the slack means is I can make this constraint more strict by 330 units, and my optimal solution will not change. So I could make this 800, I can make it 700, it won't change my optimal solution. A couple of these constraints have zero slack. This is what's driving my optimal solution in this case. Look at calcium in B2. There's no slack. I needed 40 units of calcium, I only have exactly 40. That means I can't make this calcium constraint any more strict without changing my optimal solution. If I make this 40 a 41, my optimal solution will change. Let's do that really quickly. I make it a 41. Now I have to resolve. The solver will not solve automatically. I make that a 41. Solver, solve. And look, now it cost me 322. With that restriction on calcium, the lowest I can get the price is 322. I change that back to 40. Solver, solve, and there's the 287. So slack tells you how much I can make a constraint more strict without affecting the optimal solution, and the zero slack, if there are any, tells you which constraints are driving the solution. Now there are other issues with this menu order. It doesn't look particularly appetizing, And those are what we're going